Welcome to Toddcast number 24. For this one, we're dealing with the biological aspects of stereochemistry. So it's kind of a little bit of biochem, a little bit of ochems mixed together. I'm actually not going to incorporate this into the lecture itself. So this is sort of a standalone, but this is that transition. So when you go on to take some bio classes and the terminology they use in those classes, you know how it correlates to OChem. And so it all started with Emil Fischer, famous for the Fischer projection, decided one to analyze the RNS nature, ultimately the plus and minus nature of biological compounds. And so the first one he started with was glyceraldehyde, which is actually a sugar. So what I mean by that, a carbohydrate, is it has 1, 2, 3 carbons. It also has 1, 2, 3 O's and 1, 2, 3, 4, 5, 6 H's. So it's C3H6O3, which can also be translated as C3H2O3, hence the term carbohydrate. And so his goal was to get some sort of foundation, some correlation between the absolute configuration associated with the chiral center of choice and the optical rotation, direction it rotates light. So what you're going to learn is it's going to get awfully overwhelming because we have D and L, and the reminder of that is D refers to positive or clockwise rotation. L refers to counterclockwise or negative rotation. There's also what we're going to learn, capital D and capital L, which is the stereochemistry associated with a very specific chiral center within either a sugar, amino acid, biological molecule. And then not to be misconstrued with D as a subscript here and here, just simply represents that we're using sodium light. So we're using a very specific wavelength to do this observation. This D has absolutely nothing to do with the small d, which has nothing to do with capital D, which we'll use later on. So for whatever reason, we're in love with a handful of letters in chemistry, and we use it to describe everything. So let's say that Fischer found one of the enantiomers produced a specific rotation of positive 8.7 degrees. So when he put this in with a very specific chirality, D in this case, small d, he found that it rotated light in a positive 8.7 degree direction. Okay, so is this the D or L isomer? Well, the fact that it says positive, and this is positive, means this chiral center right here, that's the one we're interested in. Just to make sure, we have an H not written in. We have an OH, we have CH2OH, and we have the aldehyde group. So we have 4 carbons, or 4 things, attached to that carbon, 4 unique substituents. So it is in fact a chiral center. And because it's positive, we call it small d. So D for dextrorotatory, or clockwise rotation of light. What is the alpha D for the other enantiomer? Well, again, enantiomers have the same physical properties. When you look in the mirror, you see somebody who has the same boiling point and melting point, but somebody who rotates light the opposite way. So if it's positive 8.7 for one enantiomer, then the other one, which in that case would be the L enantiomer, would have a negative 8.7. So it's always the opposite. So if one enantiomer is positive 8.7, the other one is negative 8.7. Enantiomers always rotate light in the opposite direction of one another, same magnitude. Okay, so want to draw stereoisomers of glyceraldehyde, and it comes down to this group here. The easiest way to do it is to leave the planar groups the same. Leave the aldehyde here, leave this carbon 1, or carbon 3, I should say, but the CH2OH group here, and switch the H and the OH. Now you notice the eyebrow up there because again it's Fischer, and this is Fischer projection. We're not going to draw the Fischer projection yet. We're going to wait till the next slide. But for this one, the OH is on what would be the right side if you're looking at it this way, or it could be on the left side. So it could be coming out with H going in, or it could be going in with H coming out. So these are our 2 groups. I want to just double check what the chirality is. So priority number 1 is O. Priority number 4 is H. So H is back, so that's easy. Priority 2 is the one with 2 bonds O. Priority 1, or 3, excuse me, is just 1 bond O. So that's forward back clockwise, so that would be R, meaning this one would be S because 4 is in front now. So this would be the R glyceraldehyde, this would be the S glyceraldehyde. And it would be specifically 2R, which is redundant because there's only one possible chiral center in this, and 2S, but again, redundant. Okay, so the Fischer projection. So same things when we squish them, the R version ended up having this chiral center right here, the only chiral in the center, so they call this D. There's also the other one that had the S chiral center. I'm gonna place my carbons a little bit better. So this is D. So this carbon right there is D. This carbon right here is said to be L. This is an R. This is an S. But we can name them a whole bunch of different ways. So this is D, but also plus glyceraldehyde. And this D is a bio terminology. So it's the same thing we do in OChem to figure out the optical rotation. It's a plus, small d, and they say plus. The big D represents at the penultimate carbon, next to last carbon in a sugar. It represents R chirality almost all the time. With a little caveat there, they prioritize a little differently. So they prioritize OH, carbonyls, other, and H, which is what OChem does. But the difference is, if we had a CH2SH, for instance, it would still consider this a lower priority than the other two. So they do slightly different priorities. Not going to worry about it for this class, but you'll need to know that for biochem. So again, this penultimate carbon, next to last carbon, because it has S chirality, it's L. Because it has R chirality, it's D. And that is almost always true. There are always exceptions to every rule, but hopefully that's when it is 99% at best. So if we draw the Fischer projection, we can also draw it this way, where we symbolize the aldehyde as just CHO, the CHOH, everything stayed the same. So again, that's still D plus glyceraldehyde. And if you oxidize it, so if I can oxidize this to a carboxylic acid and simultaneously reduce this one down to a CH3, so basically I oxidized at one center but reduced at another, you get something known as lactic acid. And what they found, interesting enough, so Fischer very much wanted D's to always be plus. That was his goal. He decided that's what it was going to be when he did his work. But when he oxidized it up to lactic acid, it ended up, the chirality, the rotation wasn't always matching up. And so what he found is, after he did enough of these like analysis of the centers, D did not always go with positive rotation, L did not always go with negative. And that we're talking about uppercase. So please emphasize that. It's the uppercase D and L that referred to an actual stereogenic center in terms of like R and S, just an alignment, whereas small d and small l refer to the rotation of light. Okay, so again, everything was measured relative to D and L. So because decided this was D for the penultimate carbon and L for that penultimate carbon, that became the norm. So just like this is D glyceraldehyde, this be D lactic acid. If you have a long chain like glucose, it'd be D glucose if the next to the last one is D. Okay, so as mentioned, glyceraldehyde rotated in positive direction, but lactic acid actually rotated in minus. So that's where just the letdown of D always being positive rotation, L always being negative rotation. That was the goal, but it failed. That's why capital D and small d, capital L and small l are different than one another. So if we did it in L, this would be capital D, small d. This would be capital D, small l. So they would not correlate. Okay, so I want to toss a few other biomolecules out there. Very important molecule, ribose. Ribose is a pentose, has 1, 2, 3, 4, 5 carbons. Ose meaning a sugar. This is a so-called monosaccharide. We'll also look at mannose. So we went through glucose before, so I'll go with mannose. It's left, left, right, right. And then this is alanine. Alanine is amino acid, has a carboxylic acid group, an amine group, an H on the central atom, central carbon, and then the side chain is just a CH3, a methyl group. Okay, so again, this is my important carbon for deciding D and L. If I do the priorities, so keep in mind, Fisher wore bow ties, so that chiral center, priority 1, 2 is the chain that goes up, there's more substituted, 3 is here. It looks like counterclockwise, but because H is in front, it's clockwise. That's an R. Want to go to Manos. And again, the priorities are 1, 2, 3, 4 for H. H in front. So again, R. And then finally, N is top priority. Carbon with it, carbonyl. That's the R group. So it's going clockwise, but H is in front. So it's an S. And a mnemonic that works with pretty much everything but cysteine. You're either a doctor or you lose. So go get your MD, your DDS, your optometry doctor, the DO, whatever it is, go get your doctorate. So either you're a doctor, DR, or you lose. D goes with R, L goes with F. That's usually the case. So even though I call it R in OChem, I would call it D-ribose. Even though I call it R in OChem, I'd call it D-mannose. And even though I'd call it S, I call it L-alanine. So D-ribose because of the R, D-mannose, S would be L-alanine. So this is going to be biochem nomenclature, the D, D, and L, but it represents the last chiral center, the penultimate carbon. There's only one in this one, so it's irrelevant. But for these, it represents the next to the last carbon or the last chiral center. Okay, amino acids, so I should mention, sugars are naturally D. Amino acids, on the other hand, are naturally L, what we find in our body. So we are built from L amino acids because they are natural. So this is alanine. And again, from the front, priority 1, 2 for the carbonyl, 3 for this. Clockwise, because H in front, it's reversed to S. So this is an S center, just like we showed over there, L-alanine. Let me do different priorities. 1, 2, 3, clockwise, but H is in front, so reverse. So these are both L-alanine, drawn in dash wedge notation, and then drawn in Fisher projection. So I want to look at a protein. So a protein is a bunch of amino acids linked together. So note that that's your first amino acid, known as L-valine. That's your second amino acid, L-alanine. That's your third amino acid, L-serine. And that last one, because here's where things differ. Although it's an R center for OChem, because according to OChem, this center right here would have priorities of 1 for nitrogen, 2 for the carbonyl, 3 for the side chain. Is that right? Well, let's double check, see if I mess this up. Carbon with 3 bonds O seems pretty good. This is carbon with 2 H's, but it has an S right there. It's covered up by my drawing. So that means I actually got those backwards for OChem. So OChem, this would be 2, and this would be 3. So it'd be 1, 2, 3. So it'd be clockwise with H and back. So we would call it R. But in biochemistry, they make the priority 2 and 3. They make the amino terminal 1, the carboxyl terminal 2, and the side chain 3. So they call this an L center. So it's an exception to the rule. Doctor Loser thing works pretty well, but cysteine is a notable exception. For anybody taking standardized tests in the future, don't know why, but this is usually a freestanding question on the MCAT and has been known to show up on a GRE from time to time. So just random piece of interest. Okay, this is kind of O-chemish and kind of biochemish, but one of the things that's often hard to do is to separate enantiomers from one another, because if they have same melting point, same boiling point, same density, same many physical properties, they're really hard to separate. And so we can't do it by normal physical means like we do in OChem lab. But if you think about it, your body can separate them. So if you ate the D and L of two different, or D and L enantiomers, two different enantiomers of a compound, your body would enzymatically recognize one and not the other. So it would actually bind one, and the other one would elute or pass through you, hopefully without going somewhere, breaking down and causing some sort of damage. But the basic gist is this, is enzymes are able to recognize one center because they are chiral themselves. So an L might fit, whereas a D may not, or a D may fit and an L may not. So they can select. So one of the early techniques that they used, and they still do to some extent, it's a little bit tricky, but when you have something really expensive, they usually employ this. We take porcine renal acylase, translation, pig kidney enzyme that adds this acyl group. So LG stands for leaving group. It's going to add a carbonyl, CH3CO, to the more nucleophilic site, which is the amine terminal. Now, because it's an enzyme, it's preferentially going to recognize L amino acids. So let me just double check again and do the first one. Priority 1, 2, and 3. Clockwise, H is in back, so that's R, so that's D-alanine, so that won't work. This alanine, H in front, so priority 1, 2, 3, clockwise, but with H in front would be the opposite. So this is my L, this is my D. When we add the enzyme in this, it preferentially reacts by acylating the L. So the L gets acylated, the D does not. So here's where it's going to take some biochem for us to do this. But this upper species, the D-alanine, has a plus and minus site, so it's called a Zweiter ion. Net charge is 0, whereas the lower one, L, doesn't have a charge on the nitrogen because those lone pairs are tied up in resonance with that O, only has a negative, so it is an anion. So there are lab techniques where we add a cation matrix, and this will bind a cation matrix, whereas this will pass through. So we can separate the charge from the uncharged. There's also something called electrophoresis, where you place it within an electric field, and the one that's charged will migrate in a certain direction. The one that's neutral will just stay in place. So we're going to separate by either affinity column, electrophoresis, some sort of charge-based technique. So I will now have D-alanine by itself, which I don't care about, and I'll have L-alanine that's been acylated, so an acyl alanine. So I need to remove it. One of the things you should remember, an enzyme lowers the activation energy in both the forward and reverse direction. So if it makes it easier to put this group on, it also makes it easier to take it off or can facilitate it. Biologically, we usually carry out, let's say, opposing pathways. You have an oxidative pathway and a reductive pathway that carry out the same basic process, like fatty acid synthesis and beta oxidation. Those two are opposites of one another. We typically, so that we can, I guess, hang on to the energy we generate or invest the energy in another molecule, we generally keep those separated so they don't end up happening in the same organelle. So we often use a different enzyme to carry out one than we do in the other. But in OChem, we're doing it in a flask, so the same enzyme can be used. So the same enzyme that put it on can help facilitate the removal of it. So note that in lab, in a flask, we can use the same enzyme. We end up with the L-alanine. It's been purified. Okay, awfully expensive and not so friendly for pigs. So over the years, starting in the 60s, they discovered it, but it really didn't catch on in vogue until probably the 80s or 90s. They started putting the chirality on lab equipment. So you could put it in a column when you're distilling. That sounds good in theory, but it breaks down at high temperature, doesn't bind as well. So that didn't work all that well, but they used it in what they call chromatography. So chromatography is a column of material that has affinity, some affinity for the compounds going through it. You pour solvent into it. So here I have this column. I'm going to pour solvent. The solvent flows down due to gravity. And then when I add these molecules, so if I put the molecules at the top here, when I add the solvent, if they like the solvent, they'll go with the solvent. If they like the matrix itself, the column itself, they'll bind and stay with it. And so in OChem, we try to set it up so that you have different flow rates. So they all come off just at different times. In biochem, you often have all or nothing. It either flushes off the column or it binds the column and then we release it later. again, techniques for down the road for you. But the basic gist in OChem is we want them to both go through the column at different rates. The problem is they have the same physical properties. So amongst those would be binding a solvent, binding a positive, or excuse me, binding a column, whatever is on it. And so what somebody thought to do is to make the column chiral, meaning on this column you put a chiral center, in this case R, with an OH. So this has an OH, this has an OH, you put an R center. Generally speaking, this kind of fits kind of like the Fisher situation. It doesn't work perfectly all the time, but it usually does. If you've ever clasped your left hand and right hand together, when you folded your hands, put your hands together, you'll note that a right hand fits really, really well with the left hand. They mesh together very, very nicely. Two right hands, probably you can't do this yourself, you're gonna need a friend to help with this, don't really mesh together that well. Two left hands don't mesh together that well. The best we get is RS. And so they learned this when they looked at looked at the physical properties of enantiomeric mixtures, a plus minus mixture, or if you will, an RS mixture. 50-50 mixture generally had a higher density, meaning they pack more tightly, had a higher melting point, harder to pull them apart, than the pure R or the pure S. So typically, R binds S and S binds R. So if I have R column, a column that has R groups all over it, this R will pass through quickly, but this S will start sticking to it and go more slowly. So when I put the R and S down an R column, you're going to find that the R comes off first. So this one elutes first, less affinity, and then the S one elutes second. So it's a neat technique for separating. So hopefully that makes sense. And the hand clasping thing really is a powerful way to look at it. Okay, other cool exceptions to the rule. So just point of interest, I was trying to tell you that our body is filled with D sugars. That's what we digest, but it ends up that in our blood type, so if you're blood type A, B, or O, it's a glycoprotein, a sugar on an amino acid chain, on the surface of your red blood cell. One of those sugars is actually an L sugar. And the logic behind having an L sugar is that we don't want to digest it. So if we don't have the enzyme to break down L sugars, it's relatively stable. Bacteria go with a similar principle. Bacteria's goal is to sneak into any host it can find and grow and grow and grow, replicate and eat, replicate and eat. Pretty simple lifestyle. So to make the cell wall, it has different fibers, different strands, if you will, that are linked by a protein connection. So the D-alanine of one side combines with a glycine residue on the other side. And it says pentaglycine, but I'm only just going to show just one of the glycines to form this glycine to D crosslink. So for instance, this is a lot of work showing this, but if you look at this residue, there's those 5 connected to a D, connected to whatever linkage is here. So this fragile little piece right here and fragile little piece right here are what's holding these fibers together. So that fiber to that fiber to that fiber. So if I were to get rid of that D-alanine, so the D-alanine is in red. So actually, let me redraw this. That's your link to the D-alanine because there's alanine. So if I were to get rid of all these red diamonds, that connection, notice that all your cross-linking just ended. So without these red diamonds, you have no connection. So if you don't have, oops, sorry, that one I didn't want to do. I'm just having fun erasing. So we notice that this fiber right here is no longer connected. There's no connection here, no connection here, no connection there. So the cell wall can't hold together. So the clever thing that, well, bacteria build this. The natural enemy of the bacteria, we're going to say, is mold, just amongst other things. But it ends up, it produced a, well, penicillin is ultimately what we're going to get to, but it produced antibacterial agent that prevented this linkage from occurring. So it actually put out something that would bind the enzyme that carried out this connection. And by not allowing this to form the cell wall, the bacteria couldn't grow. It couldn't, it was just end of the line. So a lot of our antibiotics, the penicillin-based ones, are designed to not let the bacteria grow a cell wall. And so if it can't grow a cell wall, it can't replicate, it can't keep taking over the host. So if you happen to be the host, you take antibiotics, it prevents the rapid growth of the bacteria. So there's some that are called bacteriocytic, the ones that kill bacteria. That's not the type I'm talking about. So bacteriostatic refers to ones that prevent the cell wall formation. So you have a static bacteria population that eventually dies off with the help of either your body killing it off or just a natural progression to where it dies off. If it can't replenish, then that bacteria ends up getting overwhelmed. So hopefully that makes sense. That's the biology aspect of all this. And the whole point of it was to mention that you have Ds in amino acids for the connection from one fiber to the next fiber. Hopefully this seems okay. And that ties off the bio portion of this. Next chapter, we're going to do energetics. So I will see you at the next lecture and have an absolutely wonderful time until then. Bye.